In this step-by-step guide, I'm going to run the linear models analysis that are explained in the masterclass of linear models estimation. In the first part, I'm going to run the traditional linear model analysis, and in the second part, I'm going to do the Bayesian equivalence. So I'm using the same data that is available in the practical module of week 2, and let's start with the parameter estimation of a mean. We can do it in two ways. We can do it in regression, or we can do it in t-test. So I'm going to show it how we do it with t-test. Now, one warning here. In the next week, we are going to do hypothesis testing, and JASP is designed based on hypothesis testing. So in parameter estimation, we have to use sometimes a bit tricks to get what we want. So let's go to parameter estimation of a mean, and we do it with the traditional t-test. And we have to use the one sample t-test of the classical or traditional analysis. Okay, I'm going to use of these variables I have here in my data set, academic achievement as the variable that we are interested in. And we are not going to do the one sample t-test, so we are using these in order to get the parameter estimation that we are interested in. Now, in here, additional statistics, we put location parameter and confidence interval. So that's what we want to estimate. And here we've got the results. So we are not paying attention to this part because that is hypothesis testing. Today we are doing parameter estimation. So basically what we want to estimate is the mean of the population. Now you see here there's this mean difference, but we are interested in the mean. Okay, why does it say mean difference? Because here it says test value 0. So basically what is the mean difference here is the difference of the mean of the population with 0, which in this case, if you're comparing to 0, in this case is exactly the same as the mean. So I'm going to show you that when I show you the descriptives here. So I tick with descriptives, and we've got academic achievement n equals 300, so we had 300 observations, and the mean is 50.609. And you can see that in the parameter estimation, the mean difference is 50.609. Why is mean difference here and mean here? Well, because it's the difference between this mean and the test value, which is 0. If we change the test value, then the mean difference will be different than the mean. Okay? So now we've got what we wanted. We've got the mean, which is the point estimate of the mean of the population, and we've got the confidence interval. So 49.917 to 51.300. In terms of descriptive statistics, we've got the mean of the sample, the standard deviation of the sample, and this is something I don't like about a lot of statistical software. Standard error, that's the standard error of the mean, is put in descriptive statistics. Now, descriptive statistics are about the sample. So the mean and the standard deviation are calculations over the sample. Standard error of the mean that belongs to the sampling distribution of the mean, based on this mean, of course, but it's a parameter estimation statistics rather than a descriptive one. So that's why I don't like that it's included in descriptives. But so remember that in the sampling distribution, in order to calculate the 95% confidence interval, we first calculate the standard error of the mean. Here we don't have to do it, but sometimes we report this number, the standard error of the mean, and we report the 95% confidence interval, but we don't need to calculate this to calculate that. But if you want to check, you can do 0.351 times 1.96, and then this value, so the mean minus that value is the lower bound of the confidence interval, and the mean plus that value is the upper bound. So I let you check with your calculator. It should be the same. It could be a little bit different because remember that we use the t distribution instead of the normal distribution, so it will be a slight difference, but it will be very it will approximate quite well these two numbers. Okay, so that's basically the parameter estimation of the mean. Now let's move to the model in which we have one predictor variable. So in this one we are only doing the mean because we don't have a predictor variable. When we add a predictor variable, then we start looking at the slope and the intercept of the linear model. So we go to regression and linear regression. Also remember that I told you that you can do the estimation of the mean in two ways, so the second way will be here as well. So we put academic achievement as dependent variable, and now we have some predictor variable, let's say study hours. So basically we are saying here, if we think in terms of the causal model, it would be that the number of hours of study causes academic achievement, and we are here doing the linear model in which we have this predictor. Now if you go to linear regression, here these graphs, we should have most of the information we are looking for. So when we have here coefficients, here we've got in the H0 model, this is a model in which there is no predictor variable. So that's the equivalent as the mean model that I explained. And if you can see here, the coefficient, there is only one coefficient, which is the beta 0, is 50.609, which is the mean, and it coincides with the previous analysis, and the standard error is also 0.351, which coincides with the previous analysis. Now this is what we are looking we are interested in now, the model that has one predictor. So intercept would be the beta 0, and study hours it's the beta 1, because that's how beta 1 is the change in academic achievement as a function of a change in 1 unit of hours of study. Okay, so basically we looked at the unstandardized, and I'm going to explain the difference between unstandardized and standardized coefficients. So in study hours, the unstandardized coefficient is 0.648. That means that if we change 1 hour of study hours, we get an increase of 0.648 in academic achievement. Okay, so let's, for example, if we move from 10 hours of study to 20 hours of study, this is a difference of 10 hours, then we multiply 10 by 0.648. That means 6.48. So that is the increase that you obtain in academic achievement for 10 hours of study. So if you increase 10 hours of study, then your academic achievement will increase 6.48 points. And here we've got the standard error of the estimate. So here would be the point estimate. The intercept would be 35.816 and the slope 0.648, and the standard error for the intercept is 0.834 and the standard error for the slope is 0.035. So these standard errors allows us to generate the confidence interval over the coefficient. Now remember also intercept 35.816, that means the value of academic achievement that we expect for 0 hours of study. So if our hours of study is 0, then we expect that academic achievement will be 35.816. So then after that, any hour we increase, we expect an increase in 0.648 points of academic achievement. Now we want to actually know the confidence interval before I explain what's standardized there. So if we go to statistics here and we get a confidence interval. Now we've got the confidence interval of the estimates. So remember that in this H0 model, it includes only the mean, so it's not no predictor variable. And if you see the 95% confidence interval is equivalent to the one we calculated with the previous method. And now we have the confidence intervals for the intercept, so it goes from 34.17 to 37.45, and for the slope, which is from 0.57 to 0.71. Okay, so what's the standardized and why do we have only for the slope and not for the intercept? Okay. Standardized coefficients are calculated by, before doing any calculation, we transform the variables into standardized scores or z-scores. So basically, how do we do that? In the variable, let's say study hours, we calculate the mean and the standard deviation of that distribution, and then for each of the values, the raw values, we subtract the mean, and then we divide that value by the standard deviation. So by doing that, we've got a new set of values, which are we call standardized values, and if you take the mean of that, the mean is 0. Okay, so then after we do that with both study hours and academic achievement, then we calculate the slope. Why not intercept? Well, because the intercept will be 0. By definition, it will be 0, because it will be at the level of the mean of the distribution. So that's why we don't get that is why we don't get a standardized score for the intercept, because it is 0. Okay, so what does it mean, the 0.731 standardized coefficient for the slope? Well, it means that instead of saying one increase. So what this is the increase by in academic achievement as a function of an increase of 1 hour of study. This means this is the increase in standard deviations of academic achievement as a function of an increase of 1 standard deviation in study hours. So basically, if you increase the number of hours of studies by 1 standard deviation, then you will increase 0.731 of standard deviations of academic achievement. This finishes the parameter estimation of linear models, the traditional ones. Now we move to the Bayesian version. So let's do first the t-test. We do the Bayesian one sample t-test. So we put academic achievement, and this prior and posterior sometimes doesn't work. So as you can see, it's not working, but that doesn't mean the analysis is not done. The analysis is done. We put in the descriptive plot, credible interval. So we've got here academic achievement, and that's the mean of the posterior distribution, and that's the confidence interval or the credibility intervals of the distribution. Now we want that into actual numerical values, so we've got additional descriptive statistics there, and that is all we need. So for the descriptives of the sample, we've got n equals 300, mean 50.609, and standard deviation 6.086. That's exactly the same as in the traditional approach, because there is no different analysis. When we analyze the statistics of the sample, is the same in each of the approaches. But here we've got, for the calculation of the parameter estimation of the mean, we've got this 95% credible interval instead of 95% confidence interval. And we got the lower bound and the upper bound. So here is all you need to do to get the mean in the Bayesian approach. This is the mean. Instead of being the lower bound and upper bound of the sampling distribution of the mean, this is the lower bound and upper bound of the posterior distribution.